Well, welcome back. Well, yeah. In the last video, we have just figured out, sort of, the X momentum balance for the left-hand side. As you can see, it's a pretty tedious job. But we have found out what we are doing. Okay, we have kind of figured it out, and yeah, you can feel like a marathon, going through so much mathematics at one go. Anyway, if you haven't caught any of it, you can go back and see. But yeah, this is what we are doing. We're just doing Newton's second law, and we just figured out the net force that's acting on this system. Now we want to open yet another can of worms, where we talk about the rate of change of momentum of this little box that we're talking about, the control volume. This little box. Okay. Right. So this box is what we are interested in. Oopsie there. Yeah, this box is what we are interested in. And then we are interested in the rate of change of momentum. Alright. So, how are we going to find out this rate of change of momentum? Well, as we were talking in our mass balance equations, we are talking about a system, a box where fluid enters and leaves rather freely. So fluid can enter through any of these surfaces and exit through any of these surfaces. So that is the nature of our problem. And of course, this box kind of isn't going anywhere, so to speak. So the box is stationary. Okay, if the box wasn't stationary, we'll be kind of changing our equation a bit. But thankfully, the box is stationary. Okay, for our intents and purposes. So we have a stationary box. So if we have forces acting on this box, well, somehow the momentum must change. How does the momentum change? Well, the other way that momentum can change in this box, instead of the box moving, is that the box squirts out fluid. So, okay, imagine this box was a box-shaped rocket. Okay. I'll draw a little rocket here. If you've seen those water rockets, okay, the water will be squirting out in this direction really fast. And then, when the water squirts out in this direction, the rocket ship moves in this direction. So, squirting out the forces in this direction will kind of squirting out the fluid in this direction will cause the force to be acting in this direction, so to speak. I mean, that's the idea of well, the effect of entering and exiting flows. If the flow is exiting this box, it will exert a force. If the flow is conversely entering this, then the force will be like this way. That's the basic idea of what we are doing here. Now we are going to look at our box again, a little box. Now I want to discuss two ways this momentum can change. So we have talked about the squirting bit already. If let's say you apply a force on this box, well, there are two things that can happen. The water inside this box, or the fluid inside this box, can squirt out faster. If you apply a force this way, the fluid will likely squirt out this way. What else can happen? Well, if the fluid inside the box was initially at rest, now it will be starting to move as well. Okay, so two effects that happen. One is that fluid exits the box. Effects of external forces. Fluid exits the box. And two, fluid in the box gains momentum. So these are the two effects of external forces. Now, I was saying just now, right? Let's say you have this rocket ship effect, I would say. This rocket ship effect. Alright, where the fluid squirts out this way and the force is acting this way. Okay? Now, these are two ways you can think about it. the fluid exiting the box is talking about this. Alright, so both of these, let's say the water squirting out or the fluid squirting out or the fluid entering, these are effects of the fluid entering and exiting this box called the control volume. Now, so this is just to take note that we don't double account for the same thing. So we can actually think of, these two terms as some change in momentum. Of course, you could of course think of this. You could think of this conceptually, like the rocket ship effect. You can count this as a force that's acting on this box. But you'll see that mathematically it's going to be the same. So it is so I'll have it, I'll put it here. Let's say I have this change of momentum. I put it here. Of change of momentum of fluid in the box plus effect of fluid exiting box. Okay, these two. But I can also write it as in this following manner. Let's say I only consider rate of change of momentum to be the effect of a rate of change of momentum of fluid inside the box, which is this second one. The fluid in the box gains momentum. And I bring this to the, if I bring this to the left hand side, left hand side, I'll have minus the rate of change of momentum of fluid exiting the box. So this should be what it's supposed to look like. But what do you notice? But the negative effect of the fluid exiting the box equals the rocket ship effect. Now, what was I talking about? It means when the fluid is exiting the box, it will produce a rocket ship effect in the opposite direction. So I'm going to put it this way. Rocket ship plus rocket ship effect. Okay, so they are both exactly the same, just that how would you like to consider it? How would you consider the effects of the fluid exiting and entering the box? Well, that's up to you. But I would prefer choosing this way, because if you think about the rocket ship effect, if you think about this, right? If you think about this, if fluid is exiting this way, then I'll have to say the rocket ship effect is this way, right? Newton's third law. Rocket ship effect is so-called this way. But it's very confusing to think of it in positives and negatives, so that I will just think of the fluid exiting the box this way. That will be the change in moment. If the fluid is exiting the box this way, I can just count it under here, and I don't need to change signs or anything like that. Alright. Now let's do the easy one first, the rate of change of momentum of fluid in the box. Let's do this, write it down like this. So when we talk about rate of change, we always talk about partial by partiality, the partial derivative of with respect to time. Alright. So it's the mass times the velocity in the x direction, because we are only talking about x direction momentum. So let's go. let's reduce it to density and volume, rho delta x, delta y, delta z, bullet u. Alright, so that's a very easy term. So our equation becomes like this. Okay. So the momentum of the fluid in the box will change, and then now you also have the effect of the fluid exiting the box. So what's the momentum of that that's leaving? Alright. Okay, so let's examine all of the contributions of the fluid exiting and entering all 6 phases with respect to the x direction. Let's consider these 2 phases first. 1 and 2. So the 2 phases at the side, let's consider them. So we'll copy this box over. And then, okay, there will be some fluid entering or exiting this place. So, right. And then we'll have the x-axis here. So this is at a point we call x. This is at the point we have x plus delta x. Alright. So u, which is the x velocity, will be going in this way. So yeah, what's the momentum that's leaving the box? Okay, we have to talk in terms of leaving, not entering, which again, yeah, that's the minus sign there again. But yeah, let's talk about the momentum leaving the box. Okay, so if you talk about momentum leaving the box, this is positive and this is negative. Alright, so we have to talk about the mass entering times the u velocity it has, mass entering and the u velocity it has. Okay, so this is positive, oh, this is negative and this is positive, because we're talking about the momentum that's leaving the box. Okay, fluid exiting the box. Alright, let's discuss fluid exiting the box. Alright, so very quickly, in the plane perpendicular to x, so we'll have minus minus m bullet u, the mass flow rate evaluated at x, plus m dot u at x plus delta x. There you go. These 2 other ones. So I'll need to again put it in terms of maybe a density and then okay, density and volumetric flow rate. So let's write this down. So that's rho v dot. Okay, and to make it even to change it everything in terms of velocity, because momentum, this volumetric flow rate can be expressed in terms of velocity. Okay, so that is just nothing but the u velocity times the area. And what's the area? Delta y delta z. Why? Because we are perpendicular to the x-plane. Okay, so I'm going to copy this over here. And again, I want to factorize out delta x, delta y, delta z. Okay. I want to factorize this out, so it's a lot neater. You don't have to worry about too much, writing too many terms. Okay. So this will be like so. And I have to erase this. Okay, and I change this to a u square. Or I can just leave it as a u dot u. Doesn't really matter. Okay. So that's what we have. Let's take a look. So we have already discussed the x direction, the planes perpendicular to the x. Let's see the planes perpendicular to y. Now this is slightly different. Okay, so I'm going to erase all of this. Okay, now let's look at the y plane. What's the y plane look like? It's going into the page and it's exiting at the other end, so to speak. It's a bit hard to draw. Okay, so that's the y direction. So this is y, and this is y plus delta y. Okay, hope this is not too difficult there. So again, we'll need to consider the mass and velocity with respect to the x direction. So the momentum P equals to the mass flow rate in times the velocity with respect to the x direction. So that's u. Okay, so now it's slightly different. The mass flow rate in with respect to the y direction is slightly different. So this is actually rho v dot with respect to the y direction times u, and again rho a v times u. Now this at first will look very strange. Why is there a y component velocity and then why is there an x component velocity? Well, let's look at it this way. So I'm going to put this mathematical expression to the side. I'm going to try this. I'm going to copy this box again. You have a fresh start here. So as long as you know where the coordinates are, it's fine. Now let's take a look at some cases. All right. Let's say you have a flow going into this box at perfectly parallel to the y-axis. Perfectly parallel to y-axis. Perfectly parallel. Alright, perfectly parallel. Now what's the momentum with respect to the x-axis? It's nothing. Alright, it's nothing at all because all the momentum is going with parallel to the y. There's nothing to do with the x momentum. And again, if you have flow that's entering this way with perfectly parallel to the x-axis, again the flow will just enter through this face but not through the faces perpendicular to the y-axis. So if you have a plane perpendicular to the y-axis, alright, and you have flow in the x direction, it will just go slide right past it, and it's not going to enter our box at all. So that doesn't count. Now, those are the two extreme cases where you see flows that don't actually contribute to the x or y momentum. Alright, but suppose you have a flow entering slightly oblique to it. Alright, you have a flow coming in this way, right? Oh, and then it's like, okay, yeah, you're thinking, okay, maybe, yeah, there is actually mass. Yes, there is a mass flow in, no doubt. There's a mass flow in, but also the flow is carrying momentum in this direction. So let's say this is the y, and then this way is the x, right? So the flow is entering in a very oblique direction. There is some mass flow in toward with respect to the y direction, but the flow in is actually carrying momentum with respect to the x direction. So how can we say that, well, there is a finite mass flow rate in, and it is actually contributing to the x momentum. How are we going to solve this? Yeah, so we have to look at our formula again. Momentum is mass times velocity. So this is the mass flow rate in. This m dot here is the mass flow rate in. Okay, so we'll consider them separately. The mass flow rate in will just have to do with it will be the component that comes in with respect to the y velocity. So that's v. That will help to determine our mass flow rate. But as it's coming in, we don't consider the v velocity anymore because that doesn't contribute to our x momentum. We'll have to consider the x velocity in our second part. So this is where we get our u term from, because this velocity is u, this velocity is v. So this is how we kind of account for oblique flows into this box. So we are going to make use of this principle and just write the same thing. Okay? So again, here we'll have a mass flow rate in, yep, which is this, and then the u velocity that's going in, that the flow is carrying. Alright, so again, we'll evaluate it at y. So at y, this flow is going in. At y plus delta y, this flow is going out. Okay, so that's all. So I'm just going to copy this over because, you know, I don't want to what do you call that, repeat too many things. So we'll just evaluate these two terms at the y plus delta y. And what do we have? We need a rho u, oh no, rho v this time, right? So we have a rho v, rho times v, and we multiply that by the u velocity it's having. Okay, so no problem there. Now, finally, let's see planes perpendicular to the z direction. Now, the z direction, same idea here. The mass flow rate will be simply the volume times density, right? So the volumetric flow rate, you have to do with the z velocity. In the z plane, all right, z plane, we'll just have the mass again times u, and that will be equals to rho a w times u. Okay, so I'm going to write that down. generic formula equals rho A W times U. Okay, so I'm just going to write it this way. Copy and paste again, just to save time. Z plus delta Z. Oh yeah, this should be with respect to Y. Why? Why is it with respect to Y? Because the area is delta X and delta Z. Alright, so this should be Y. Now, what are we doing here? Z plus delta Z. So I'll need a W velocity, which is the velocity in the Z direction. And this is what our equation will look like. Now, just plug everything back. Plug everything back here, and we'll get this. Plug everything back, and we get, okay, we will get this term plus this term plus this term. Okay, so just to recap, why are we talking about fluid exiting the box this time? Because we are talking about things in this way. This is the force, which is the cause. So the force acting, let's say, the force acting on the box, the summation of all forces, the net force acting on the box. Let's say, let's give it an arrow. This, let's say, this arrow forces, all the forces acting on the box will cause a change in momentum. Let's put the arrow and make it green. The force entering the box, so to speak, or force acting on the box, will cause a change in momentum. And the momentum is so called like the effect. That's the effect. Alright, so the forces are here, the cause. Then these are the effects. The effects is that the momentum kind of has to change. So that means the momentum in the box either changes, the momentum in the box changes, and the momentum, like the X momentum exiting the box, also changes. So this is what we are doing. Okay, so we're gonna stop here. We're almost done with our Navier-Stokes. You just have to have a few more manipulations, then we're done. Thanks for watching. I'll see you in the next video.